Hi, and welcome to this lesson on receivers. In previous lectures, we have discussed some of the key concepts associated with receivers. For example, we've probably talked about frequency conversion, and we've probably said something about single conversion superheterodyne architecture. Now, that leaves a lot left to cover, so in this lesson we're going to start filling in some of those gaps. First, I want to give you an idea about all the possible ways that receivers can be implemented, and by that I mean receiver architectures. There are many possibilities beyond single conversion superhet. These include direct sampling, tuned RF, other superhet architectures, and direct conversion. As we go along, I'll introduce the concept of frequency planning. Whenever you have frequency conversion within a receiver, it brings up the question of frequency planning. That includes questions like, what will the local oscillator frequencies be? You may recall from the lesson on frequency conversion that low side and high side injection are options, and so these, among many other options, may be things that you need to consider. There are also lots of pitfalls, and one of these, for example, is the notorious half IF problem, and I'll briefly describe these problems. Now, it's likely that viewers are coming into this lesson from a variety of backgrounds. Let me say that you don't need to be an electrical engineer or have electrical engineering background to get the principal points of this lesson. However, I'm going to use some terms that you may not know already, so let me briefly address those. The first one is about analog to digital converters, or A to Ds. I will frequently refer to the term Nyquist zone, the Nyquist zone of an A to D. All you need to know about Nyquist zones is this. The first Nyquist zone of an A to D is from 0 Hz to 1/2 of the sampling rate, f sub s. That's the range of frequencies over which an A to D can sample a signal without aliasing. The second Nyquist zone of an A to D is from 1/2 times the sample rate to 1 times the sample rate. That is fs divided by 2 to fs. It turns out that it's also possible to properly sample a signal if it exists completely within the second Nyquist zone. But the signal must be properly filtered at the input of the A to D, and the resulting digital version of the signal will be spectrally reversed. Nevertheless, using the second Nyquist zone of an A to D is totally possible and sometimes desirable, as we shall soon see. The second thing that will come up is some discussion of linearity. In particular, I'll mention IP2, which stands for second order intercept point. Now, this is simply one way that we quantify the linearity of a receiver. Higher IP2 is more linear. For the purposes of this lesson, all you need to know is that the nonlinearity of receivers results in harmonics, which are copies of the signal at integer multiples of the original center frequency. The third thing that will come up is the distinction between differential and single-ended signals. Now, this topic is completely in the weeds unless you fancy yourself an electronics engineer, but it's useful to know that differential signals enjoy some advantages in receiver design, and these include improved linearity and improved immunity to internal interference. Now, if any of these three things, Nyquist zones, linearity, differential signals, are mysterious to you, don't worry. Really, all you need to make sense of this lesson are the concepts presented in the previous lesson on frequency conversion. If you've seen that lesson, you're good to go. Okay, with that, let's get started.
So first, direct sampling. Direct sampling architecture is very simple. We have an antenna, we have some pre-selection or selectivity, we have an amplifier, that's the gain, that's that 50 to 110 dB that we typically require, and then the digitizer. And the rest is done in DSP. So here there's no frequency conversion. There is just filtering, that is selectivity, gain, that 50 to 110 dB that it takes to get from a typical signal level up to the level that an A to D can productively digitize, and then the digitization itself. Now note this is a simplified diagram. Usually there's several filters, one doing pre-selection, there's multiple gain stages, there's anti-alias filtering separate from the pre-selection and so on. But there is only filtering and gain and not frequency conversion. Now one variant of this is low-pass direct sampling, where we're using the first Nyquist zone. Now this is rarely used for communications applications because it requires very high second order linearity, because there's potential for signals in the first Nyquist zone to create second order harmonics, which appear both in the first and second Nyquist zone. A more common architecture to use these days for direct sampling is bandpass direct sampling, and that's where we use a Nyquist zone greater than 1. For example, the second Nyquist zone. This has the advantage that signals in the second Nyquist zone alias to distant Nyquist zones, so that the requirement's second order linearity is much less. Tuned RF. This is basically the analog version of low-pass direct sampling. So here you see an analog detector instead of a digitizer. Many challenges in tuned RF architecture, so it's not very commonly used. For example, filters must have very small fractional bandwidth. That filter here must provide all the selectivity that's required at the RF frequency. The detector has to perform well at the RF frequency. See, most detectors, like AM detectors and FM detectors that are analog, work much better at lower frequencies. Furthermore, it may not be possible to implement the necessary gain, and this is because of instability due to interstage feedback. See, if I have a long string of amplifiers, it's difficult to keep the RF from feeding back through the power supply, so this is a recipe for instability. So having that 50 to 110 dB of gain or so, all at the same frequency, turns out to be a challenge. Single conversion superhet architecture. In this case, we have an antenna, we have pre-selection, we have gain, at least some fraction of the gain. Then we have a tuning LO doing frequency mixing, and then a lower IF stage, an IF at a lower frequency, where we have some more of the selectivity and some more of the gain. And then we can be either digitizing, that's IF sampling, or doing analog detection. Either one is common. Here it's easier to achieve the necessary gain without interstage stability problems. The reason is because RF that ends up in the power supply from this amplifier, well, it can make it back to this amplifier, but if it makes it back here, it's at a different frequency, so it's less likely to cause a problem. We also have better selectivity because the IF filter is easier to implement. The fractional bandwidth at IF is greater than the fractional bandwidth at RF, and that allows us to make a more selective filter. Furthermore, we have more options for technologies at lower frequencies. As we go down to lower and lower frequencies, there are more and more schemes, many of them having low cost, for implementing filters. Furthermore, it facilitates the use of standard IF frequencies. I'll say more about this throughout the lecture, but the idea is that the industry has gravitated towards a limited number of frequencies which are used for IF purposes, and that means that there are lots of off-the-shelf filters available for those particular frequencies. So here's an example, an FM broadcast receiver. FM broadcast exists at frequencies from 87.5 to 107.9 megahertz. Each FM signal is about 200 kilohertz wide. In this particular example, I'm going to use low side injection to get the signal to a center frequency of 10.7 megahertz. Therefore, that's the IF frequency. The bandwidth now at this IF represents a fractional bandwidth of 1.9%, which is totally manageable from a filter design perspective. The LO tuning range, since we're using low side injection, is from 76.8 to 97.2 megahertz. The image band goes from 66.1 to 86.5 megahertz. Those are determined in the usual way. Now note, from here we can see why 10.7 is about the lowest IF that we can imagine using for an FM broadcast receiver, at least for a single conversion superhet. And that's because if we made the IF lower than 10.7 megahertz, this would creep up and eventually intersect the RF band, which would make it impossible to separate the image band and the RF frequencies. And we know that there's no way that we can eliminate an image after frequency conversion. So because 10.7 is the lowest frequency, which is practical for a signal conversion superhet for FM broadcast applications, and because FM broadcast is so common, 10.7 megahertz is a very common IF frequency for all applications. The half IF problem. This is characteristic of all superhet architectures. The idea is this. Let's imagine we're doing low side injection. The problem also exists for high side injection. but we'll talk about low side injection first. The RF frequency goes to the IF frequency, and the IF frequency is simply the difference of RF and LO. However, what happens if we apply a signal, or a signal exists, at a frequency of RF minus IF divided by 2? Well, in that case, we see that the output goes to IF divided by 2. Now, if there are no other impairments, that's fine. That will not cause a problem. However, if we have a limited second order linearity, then we will get a second harmonic associated with that signal, and the second harmonic ends up at the IF frequency. So the half IF problem is that there are signals at this frequency which, because of the limited linearity of these stages, results in a signal overlapping the desired signal. So this is dangerous because it may be too hard to get RF minus IF divided by 2 adequately rejected by preselection. It's also dangerous because mixers and amplifiers have limited second order linearity. And finally, it's dangerous because the subject spurious product cannot be filtered out once it's generated. In other words, once we have this, we're done. It's going to be in the output. So here's an example of the half IF problem affecting a broadcast receiver. Same receiver we talked about in the previous example, taking this tuning range, putting one of those 200 kilohertz signals at 10.7 megahertz, using low side injection. Well, from the equation we just worked out, the half IF frequencies are in this range. Note here that it is impossible to filter all the frequencies vulnerable to the half IF problem by fixed preselection. Possible remedies, again, make sure you have adequate second order linearity at the IF stage, or increase the IF center frequency, because if the IF center frequency goes up, then these frequencies will go down. So this is strong incentive to use higher IF frequencies. With this in mind, we come up with the dual conversion superhet architecture. So in dual conversion, we have 2 frequency conversions, 2 IFs. The first IF we land at using a tuning LO. So this much looks very similar to a single conversion superhet, but then we do one more conversion to get to the final output frequency, and that can be done with a fixed LO. This makes it even easier to achieve the necessary gain without interstage stability problems. Why? Because now we have 3 stages over which to distribute the gain that we need. We've got a higher first IF, so this IF can be higher than the IF that we would need for a single conversion superhet, and that facilitates larger tuning range, and it's easier to manage the half IF problem that I just talked about. And then finally, because we have a lower final IF, we have larger fractional bandwidth for this filter, and that means better selectivity, or at least the potential for that. So here's an example of an FM broadcast receiver using dual conversion. The first IF, we could go to 10.7 megahertz. The second conversion, we could go to 455 kilohertz, which is a fairly common final IF for a dual conversion superhet. Note the first LO tunes, the second LO is fixed. Either LO may be low side or high side. However, I'll tell you, if you do both high side, you've got a huge advantage in that you get all the advantages of high side injection, which I've talked about in a previous lecture, and the spectrum comes out facing the right direction, because this gives you a spectral reversal and this gives you a spectral reversal, so the output signal is correctly oriented. And then if I really had a big issue with half IF problems, I could increase this frequency, leave this the same or increase it, and thereby adjust the requirements that I have for these preselection filters and for this filter. Now, contraindications for this approach, why we might not want to do it? Well, it's starting to get expensive now because we have more parts and we have 2 LOs. In fact, that second LO is going to account for a big chunk of power consumption because LOs ordinarily account for a large fraction of the power consumed by a receiver. Here's yet another example, a GSM base station receiver. GSM is a cellular protocol, becoming less common these days, but still appears in a big chunk of the world. Let's say we have this frequency range, and we want to produce a signal here. Well, one way to do this is to go to an IF of 240 megahertz and then to an IF of 10.7 megahertz. That puts image frequencies in the range 389 to 414 megahertz. And this scheme is very commonly implemented. So this is a very common scheme for moving this range of frequencies to a digitizer with a center frequency of 10.7 megahertz. In fact, I can think of many base station receiver designs I've seen that use exactly this scheme. Another common version of this design uses a third conversion to go to 455 kilohertz to further improve selectivity. So very, very high performance GSM receiver might have three conversions: 240, then 10.7, and then 455 kilohertz, again to spread all that gain out over four different stages and to achieve the best possible management of all the spurious products that might result. Now, up-down architecture. In up-down architecture, the first IF is above the tuning range and the second IF is below the tuning range. This is appropriate when the tuning range must be very, very large, at least on a fractional bandwidth basis. So for example, HF general coverage receivers, this is a receiver which goes from 3 to 30 megahertz, requires up-down architecture because there's no way to tune from 3 to 30 to some IF below 3 megahertz without a conflict in preselection or image rejection. Similarly, spectrum analyzers use up-down conversion. Multiband receivers are fairly common. Let me show you an example of multiband receiver architecture that might appear in land mobile radio. In land mobile radio, there are actually several bands which are commonly used, and in some applications, such as police communications and government communications, you have to be able to operate on both bands. So let's say you have to operate on 138 to 174 megahertz and also 406 to 512 megahertz. Well, to have one receiver that does both using the same architecture can result in reduced performance. So what you can do instead is divide and conquer. So for example, 138 to 174, you could convert to 10.7 using a tuning LO covering this range. And to cover the higher frequency band, you could first go to 70 megahertz using this LO tuning range, and then by mixing with a fixed frequency of 59.3, end up at 10.7 megahertz. And then you just select one of the two. From there, then you could go to 455 kilohertz. So that's an example of a divide and conquer architecture. Direct conversion architecture. In this case, we have an RF section, and we use quadrature down conversion to obtain I and Q, which is then digitized. The advantages of this technique are very large tuning range. We're not impeded by the limitations of a superheterodyne architecture. There's no image band because there's no IF. The minimum IF frequency is achieved. That is a frequency of 0. It's low cost and low power. These are all great features of the direct conversion architecture. However, there are also many disadvantages, and this tends to keep direct conversion from showing up in all but applications in which cost and power must be absolutely minimized. So here are the contraindications for direct conversion. First, the LO frequency is equal to the RF frequency. This means the LO easily leaks out the input. Your receiver should not be transmitting. Furthermore, the LO re-enters the mixers, appearing as a DC-centered tone jammer. Next, direct conversion is critically dependent on IQ balance, that is gain and phase balance, and the performance of the Quadrature LO generator, which needs to produce very precisely signals which are 90 degrees out of phase. So this usually means that in situ calibration is required. You can't just assume that whatever you build is going to be sufficiently accurate. Typically, when the radio is running, there has to be something which is tweaking up the IQ balance and tweaking up the LO phase quadrature. As a result, it's very difficult to achieve large bandwidth in direct conversion architecture. Analog complex baseband processing exposes the signal to low frequency interference within the radio. There is tons of low frequency interference within a receiver. For example, modern power supplies produce tons of noise at frequencies not too far from DC. Furthermore, everything that's digital tends to produce a lot of noise. And all these signals will then overlap into the IF, which is centered at 0 Hertz. This is not a problem with IF sampling architectures utilizing superheterodyne techniques. Finally, all gain must be implemented either at RF or at baseband. There is no possibility of distributing gain at other IFs, at least as I've shown it here. That means baseband gain, the gain at the IQ stage, must be implemented with extraordinarily high second-order linearity. So this is perhaps the biggest problem of all for direct conversion. Now, having said that, the popularity of direct conversion is actually increasing as the years roll on. One reason is that this issue with IQ balance is becoming increasingly easy to address using CMOS RFIC implementations. See, CMOS is the same stuff that people make computer circuits and DSP out of. So if you can put the RF on the same chip as a bunch of DSP, then the process of doing this calibration can be made a lot simpler and a lot more accurate, and also done more cheaply. Then these two problems are addressed by sound differential design. Because remember, differential design has intrinsically good common mode rejection performance, and good differential design has intrinsically good second order linearity. Now, a modification to the direct conversion approach is near zero IF architecture. If you look at this, it looks very similar to direct conversion. The difference is that the RF is offset from the LO by about half the bandwidth. So instead of going from RF directly to DC, instead you put the signal here, just above DC. So all the problems that we have around DC, including the LO tone jammer, are down here, whereas most of the signal's up here. So that's a near zero IF architecture. And this has a lot of advantages, especially since these days it's not much difficulty here to do that final shift of the signal to zero IF using DSP. Finally, let me show you a scheme that combines all the advantages of superheterodyne architecture and all the advantages of direct conversion architecture, and that's superhet plus quadrature conversion. And the idea is exactly what the name suggests. We have a superhet that goes to some IF, and then we do direct conversion from the IF. This combines all the advantages of superhet architecture with direct conversion architecture. Also mitigates many of the disadvantages of the two architectures. And finally, I should point out here, I'm showing superhet architecture with just one frequency conversion, but in fact there could be any number of frequency conversions there. It could be up, down, and so on. The idea here is simply to combine superhet for the first few stages with a direct conversion for the final stage. Finally, frequency planning. Frequency planning is the process of selecting IF center frequencies and injection modes. In other words, where we're going to do low side injection versus high side injection. As we've seen, these choices have implications for pre-selection, for image rejection, and for post-mixer spurious filtering. And these frequencies and the expected levels of key spurious signals are determined using this process of frequency planning and used to set specifications for filters and linearity specifications. So here we see all these things coming together, and we see that they're related. Bandwidth, linearity, frequency plan, all these things are requirements which interact with each other and have to be traded off. Frequency planning can become very challenging for receivers operating in crowded spectrum, especially when multiple conversions are required. So frequency planning for multiple conversion superhet receivers can become very complicated. Certain standard IF frequencies are preferred so as to benefit from off-the-shelf filter designs. So the two common ones I've shown several times now are 10.7 megahertz, 455 kilohertz. Other common IFs include 45 megahertz, 70 megahertz, 140 megahertz, and there are a few other common IF frequencies which are a little bit more application specific.
And with that, it's time to wrap up. This lesson has been primarily about receiver architectures and is intended to give you some idea of the issues that go into designing receivers and subsequently the performance of receivers. It should now be obvious that there are many pros and cons that must be balanced, and this needs to happen also within the constraints of size, weight, power, and cost. This often results in some uncomfortable compromises. And before signing off, I must point out that we have not yet addressed a very important issue about receivers, and that is sensitivity. That is, I have not yet said anything about how we can know the minimum signal power that a receiver can effectively receive. To be sure, sensitivity is a critical issue, both for receivers and for radio link planning. So much so that this topic deserves its own lesson. So look forward to a discussion of sensitivity in a future lesson. That concludes this lesson on receivers. Thanks for listening.